Hello everyone. My name is Michael from Bright Expert Statistics Services and the University of Nairobi. This research poster is for a study on modeling greenhouse gas emissions by Kenya's agricultural sector for forecasting future values. A comparative analysis of autoregressive integrated moving averages, ARIMA, error, trend and seasonality, ETS, and neural network autoregressive NNAR models. The motivation behind this study is the urgent global concern of climate change and global warming, largely driven by greenhouse gas emissions. Agriculture is Kenya's largest contributor, accounting for about 62.8% of the country's emissions, mainly from use of nitrogen fertilizers and rearing of ruminant livestock. Although Kenya is not among the top global emitters of greenhouse gases, the country has pledged to cut greenhouse gas emissions by 30% by 2030. To monitor progress toward this target, we need accurate models for forecasting greenhouse gas emissions by the agricultural sector in the country. The main objective of this research was to compare three forecasting models, ARIMA, ETS, and NNAR, to determine which one provides the most accurate forecasts for greenhouse gas emissions by Kenya's agricultural sector. We used time series data from the IMF covering 1970 to 2024. To identify the best model specifications, we applied a Kaiki Information Criterion, AIC. We tested residuals for independence, constant variance, and normal distribution properties. Model validation was done using a train test split method implemented using the 80-20 rule. Specific metrics used for assessing forecast accuracy of the models were rooted mean squared errors, RMSE, mean absolute errors, MAE, mean absolute percentage errors, MAPE, and mean absolute scaled errors, MASE. The Diebold-Mariano test was applied to check whether differences in forecast accuracy identified between models were statistically significant. Since the raw emissions data was skewed and non-stationary, we applied a logarithmic transformation and differencing to stabilize the series. Our analysis found that the RAIMA 0-1-0 model performed well with the lowest RMSE. The ETS model, with multiplicative errors, an additive trend, and no seasonality, performed equally well, with slightly better MAE, MAPE, and MASE values. The NNAR model performed poorly in comparison. Statistical tests showed no significant difference between ARIMA and ETS, but NNAR was significantly less accurate. We therefore concluded that ARIMA and ETS models are more reliable than NNAR models for forecasting greenhouse gas emissions by Kenya's agricultural activities. For Kenya's 2030 emissions reduction goal, ARIMA and ETS models provide suitable tools to monitor and project progress. Future research should test whether NNAR models may perform better than ARIMA and ETS models in other agricultural settings or countries, and for larger data series like those of monthly or quarterly GHG emissions. Thank you for your attention. For corroborations or any inquiries regarding this study, please feel free to reach out using the contact details provided on the poster.